Hello everyone. So today we're going to start on 9.2. In 9.2 we're going to talk about very specific, very special kind of vector field called conservative vector field. So it's all come from chapter 8. So in chapter 8 we learned that for some vector field F, it is possible to alter the path of a line integral without changing the value of the line integral. Without changing the value of the line integral. And which is extremely surprising because, as you might expect, a line integral, the value of a line integral is usually dependent on two things: the vector field f and also the path that you take. So for some vector field, we actually allow us to change the path, and yet without changing the value of the integral. But of course, there's certain things that have to be constant. So without changing the value of the line integral, as long as the new path share the same starting points and ending points. So even though the path is different, we still require the path to start from the same point and end at the same point in order for the line integral to remain the same value. And you actually remember seeing that in chapter 8, implying that this type of vector field, it really doesn't matter what the path is, because the value of the line integral is entirely dependent on the beginning point and the end point. Okay, this vector field is extremely important because it allows us to evaluate a line integral quicker or easier by substituting a simpler path instead of dealing with a path that's difficult to deal with. So a vector field with this property is very important because it makes evaluating a line integral easier to do. And the way to do that is by allow us to change the path to something that wherever we choose. This type of vector field is called a path independent vector field. A vector field F is called a path independent vector field if its line integral has the same values for all paths from, let's say, vector A to vector B. So this is called a path independent vector field. If you can evaluate every single line to go within this vector field, as long as they all go from A to B, they all have the same exact value. And this is a vector field, you actually already have seen it because you saw it in chapter 8, theorem 9.2.1, which states the following: if the line integral integral over alpha vector f dot d vector x of a vector field F is independent of the path alpha from let me make more room, of the path alpha from A to B, then this vector field, which is what we call path independent vector field already, we all know that, but it has a second name. This vector field is called a conservative field, or a much better name, or a gradient field. So therefore, I just introduced three sets of terminology. They all exactly the same thing. If you say a vector field is path independent, that means it is conservative. That means it is a gradient. And because of the fact that this vector field f is a gradient, therefore there exists a real value function f of vector x such that this is true. The gradient of lowercase f of vector x is equal to vector f of vector x. So therefore imply that if you have a path independent vector field, or a conservative field, or a gradient field, remember these three words are all exactly the same. If you have that, there must be an quote-unquote antiderivative of this vector field. And that's what the lowercase function f is. And this lowercase function f has a name. The function f of vector x, lowercase function f of vector x, is called the potential function of vector f of vector x, or sometimes is referred to as the field potential. Oops. Of vector f of x. So sometimes it's called a field potential, but sometimes it's just referred to as the potential function. So therefore, what I introduce as the following words: path independent. That means that when you have a vector field, all line integral that go from A to B, regardless what the path is always the same exact value. And when you have a path independent vector field f, then that means that vector field f is a conservative field as well as referred to as a gradient field. And because it's a gradient, therefore it must have a quote-unquote antiderivative of that. And that is called the potential function. Now, since I already mentioned to you that path independent or conservative field, now that we have the correct terminology, is important, there are two major questions that we try to figure it out. So since conservative field are important, we want to figure out the following two questions. Oops. So what two questions? Number one, if you're given a vector field f, how to determine if it is conservative or not? I mean, clearly, it's probably not a good idea to try to randomly evaluate multiple different lines to go from point A to point B and see if they all give you the same value. The problem with that is that even if you can test like 10 different value, 10 different line integral, or 20 different line integral, and they all give you the same value, there's no guarantee that the 21st or the next one that you do would give you the same value. And even if all the vectors go from point A to point B would give you the same line integral value, there's no guarantee that if you go from point C to point D, it would be the same. There are just too many things to check. So there must be a better way to determine if it is conservative or not. And so that's the first question. Now, what if we can actually identify that it's conservative? What's next? Well, if vector f is conservative, then the next question is how to find its potential function. F of vector x such that gradient of f of vector x is equal to vector f of vector x. Because based on fundamental theorem of calculus, you learned that you can actually evaluate the line integral of a gradient field, which is basically a conservative field, by simply evaluating the potential function at the two endpoints and subtract. So therefore, if I can actually find the potential function, then I will be able to just use fundamental theorem of calculus to calculate the line integral. Then I don't even have to deal with the line integral at all. So let's tackle these two questions one at a time. Let's start with the first question. How to identify a conservative field? So to do that, we actually got to make use of something that we have learned in 9.1. So what did we learn in 9.1? Well, green theorems. So imagine the following. Let's say we have a vector field F in R2. Okay? And let's assume that F is a conservative field. So what we're going to try to do is try to figure out if there's some special property about a conservative field that we can use to identify it. So imagine the following. Let's say we have point A and point B. And now I'm going to define two separate paths that go from point A to point B. Let's say one of them go like this. And we'll call this one alpha. And then let's say we have a second path that go from point A to point B. I'm going to call it beta. Because of the fact that f is conservative, it implies that the integral over alpha vector f dot d vector x should equal to the line integral over beta, because f is conservative, is path independent. So since alpha and beta both have the same beginning endpoints, both of these line integrals should result in the same exact value, regardless what the path that we take. And some of you might already notice, if you look at these two paths that go from both from A to B, they actually form a closed loop. Note that alpha and beta kinda form a closed loop. Well, why did I say kinda? Because they actually don't form a closed loop the way it's written. Why not? Well, because it doesn't follow the correct orientation. So what I'm going to do is the following. Let's see if I can do this. I can now form the closed loop by doing this. by, let's see if I can do this. There you go. There you go. By taking beta, but reverse the direction of beta. If I do that, now all of a sudden I have a closed loop with an enclosed regions R in between. So therefore imply that they form a closed loop, which is alpha, union beta negative, will form a closed loop or closed curve with R being the bounded regions. Now let's take a way to think what's happening here. Now, what if I'm trying to calculate the closed curve integral? Now, let's try to evaluate the closed curve integral of this closed curve. So I can calculate this closed curve integral two ways, just like what we talked about back in 9.1. I can either separate this closed curve into multiple curve and then evaluate each of the curve, or because a closed curve integral, I could actually use Green theorem to do it. So let's say we let f equal to basically f1 comma f2. Now I'm going to try to evaluate this closed curve integral. So first way is to basically just evaluate line integral by separating into two curves. So basically meaning that I'm going to evaluate this closed curve integral of alpha union beta negative f dot d vector x. I can separate it into two separate line integral. One of them is alpha, one of them is beta negative. And here becomes something very interesting. Based on theorem 9.1.1, if I find the line integral of a curve or reverse of a curve, I can actually think of it as just the negation of the line integral of the curve itself. So therefore I can say that that's just the same thing as my alpha line integral plus negative the line integral over beta f dot d vector x. By reversing the direction of the curve, I have to introduce a negative into my line integral. So therefore, it seems to me that this line integral would equal to this. And here comes the important part. Because we know that f is conservative, we know that these two line integrals have the same exact value. So therefore, when I subtract them, I actually get 0. As a matter of fact, a very interesting property of conservative field is this. For a conservative field, all closed curve integral is always equal to 0. Because every closed curve integral will have to be basically two curves that go from the same beginning point to the same end point, but just take different paths, but one of them have to go in the opposite direction. So that's good. That's a result. That's something special that we can use. Because for most other vector field, when you do a closed curve integral, you could get any kind of result. But for a conservative field, you only get 0 result. Now comes the big question. What if I try to evaluate it, but using Green theorem instead? What does Green theorem tell me? Well, let's find out. So this one is doing line integral. Now we're going to try to do green theorems. So green theorem says the following. So we have the line, the closed curve integral of alpha union beta negative. So that's the same thing as saying that we're doing the boundary of R. Because remember, I defined the interior to be R, so therefore the boundary would just be dr. And according to Green theorem, that would be the same thing as a double Riemann integral over R, df2 over dx minus df1 over dy, dA. So that would be what the line integral, the closed curve integral would give me if I were to use Green theorem. But we already established the fact that this closed curve integral have to be 0. Therefore imply that if I do this Riemann integral, I will simply just get 0 as a result. Remember, this closed curve integral should not give me different value based on the way we calculate it. So when we calculate using line integral and realize that it always comes out to be 0, then if I apply Green theorem, I should also get 0. Now comes the big question. If I'm doing this Riemann integral and I get 0, no matter what regions we use, what is the logical conclusion? The logical conclusion is this. This statement implies that we have an integrand that is equal to 0. And that is something that we can use. Now we have something that we can use to define a conservative field. Definition. Given a vector field, a function, a vector field vector f of xy, which is equal to f1 of xy, f2 of xy. If df2 over dx is equal to df1 over dy, then the vector field f is conservative. And this expression df2 over dx equal to df1 over dy is often referred to as, is called the consistency condition. So when a vector field f satisfies the consistency condition, then it must be a conservative vector field. Sometimes the consistency condition can be rewritten as what you see right here, but it's usually easier to just move the df1 over dy to the other side and just test whether you have an equality between these two partial derivatives. Now, I'll show you a very simple example to illustrate, and that might be the last one we're going to talk about today, and then we'll continue on our second question in the next video. Is vector f of xy equal to negative yx a conservative field? So how will you go about doing this? Well, the first thing is you identify that this is my f1, this is my f2. And now all you have to do is just test the consistency condition, then you see what happens. So I'm going to go and do df2 over dx. So that will be d over dx of x, which come out to be 1. And I'm going to do df1 of dy over dy. So that's d over dy of negative y, which come out to be negative 1. So now we have a result. So df2 over dx seems to equal to 1, which is not the same as negative 1, which is equal to df1 over dy. So therefore, in this case, the consistency condition is not met. So therefore, in this case, f of vector f of xy equal to negative yx is not conservative. Now let's try a second one. How about this one? Is f of xy equal to 2xy squared 2x squared y? A conservative field. So once again, this is my f1. This is my f2. So let's go for it. So df 2 over dx would equal to d over dx of 2x squared y, which come out to be 4xy. And df1 over dy would equal to d over dy of 2xy squared. So that also come out to be 4xy. So therefore, I can now conclude that in this case, df2 over dx is actually equal to 4xy, which is equal to df1 over dy. So therefore, the consistency condition has been met. So vector f of xy equal to 2xy squared, 2x squared y is actually conservative. Now, what is the result? Once we know that it's conservative, it implies that this function vector f, 2xy squared, 2x squared y, must be the derivative or the gradient of some function. And that function, which is called a potential function, must exist. And we just have to find it. And that would be the focus of our next video. So that's it for today. We'll continue some more on our next video, okay? Talk to you guys then. Bye-bye.